My name is Selvakumar, and I work as senior software engineer for Juniper Networks. So today we are going to talk about why 5G is fast. And I promise there is C++ in this talk. So agenda. So unlike my previous talks, this talk is a bit different. Typically, what the talk I give is about some problem we faced at work and how we solved it using some design patterns or some techniques in C++. But this talk is not going to be like that. This talk is not something I did at my work. This talk came out of my hobby work, which I started doing with 5G. I do some work on 5G in my office as well, but so this talk is from my hobby, and I hope this leads to a series of talks where I explore what can be done in 5G using C++. So there are two parts to this talk. The first part, we will try to answer the question why 5G is fast. And the second part, I think it's going to be more interesting because there is some C++, but unfortunately it's not much, but there is some C++, and there are some very interesting motivational examples of how we can use ORAN and C++ and create some very unique solutions. Don't worry about the abbreviations ORAN, we will come to it. Okay, so between part one, part two, there will be a short break. If there are any questions, we can answer that. Then at the end of the talk, we can answer further questions. Yeah, let's start. Why 5G is fast. So a few months back, with a group of friends sitting around and we were just chatting after dinner. And somebody asked me, hey, you work for a networking company, so tell me why 5G is fast. So I thought about it, and there is no easy answer to it. Because what do we mean by fast here? So I had to take a step back and think about throughput and latency. So when somebody says fast does not mean anything if you think technically, right? So fast typically means that throughput. When people say about something is fast, they're talking about throughput in some context. Where so there's an informal definition of a throughput. So throughput is something where you say that in a given time window, how much unit of data is transferred. So if you say that I have a throughput of 1 Mbps, which means in 1 second time window, we can send 1 megabit of data. Now, latency. So in some context, fast means low latency. So what is latency? So latency is, again, it's an informal definition where you say that for any unit of data, time taken for the unit of data to travel from one network node to another network node. So this unit of data could be your UDP packet, or it could be your request. So you say that latency of, for example, you say my client server network latency is 10 milliseconds, which means you are saying that for every request from my client to reach server, it takes 10 milliseconds. And obviously, latency and throughput are not the same. So let's go back and see why 5G is fast. So maybe I think we have to rephrase this question. This is not probably the right question. So what we have to see is why 5G has higher throughput and ultra low latency. Now, this is more meaningful question, which probably we can try and answer. Right. Okay, so just one slide to show from where the 5G came. So 5G technologies developed by an organization called 3GPP. So 3GPP stands for Third Generation Partnership Project, which consists of 7 telecommunication standard development organizations. So all the major standard development organizations are part of this 3GPP, and they put out specifications, and they do a lot of research, and they define all the technologies. So these technologies are used in mobile communication. So 4G, 5G, and whatever comes next, it's all put on by 3GPP. So the first release of 5G, which we call 5G today, it's basically release 15, which was done in March 2017. So this is called the first drop. But the real game changer of 5G was release 15, which is called main drop, which came in September 2018. So here, all the physical network protocols were finalized. So now, September 2018 was very good year for 5G. This was the first time in a real scenario. It was done in labs previously, many years ago, but in the real scenario, real deployments started happening in 2018. Then we had a final drop of release 15 in 2019. And throughout 2019-20, we had different drops of release 16 and 17. And the current release is release 18, and there are different drops of release 18 starting from 2021. Now, I have given references, so interested people can go and look into the documentation and see what each release added to 5G. But this is just an information slide to know that what are the releases and who does this. Okay. The important thing in 5G is spectrum, of course. So typically all mobile communication, right, from 1G, 2G, 3G, 4G, it happens between 450 megahertz and to 6 gigahertz, and 5G also uses the spectrum. But the 5G frequency bands are closer to the 6 gigahertz range. It's from, I think, 3.9 gigahertz, and there are several bands which are closer to 6 gigahertz, and the older technologies, older generations are closer to the lower end of the spectrum. And because 5G has very demanding use cases and demanding goals, like extremely high bandwidth and ultra low latencies, to support these use cases, in addition to this 450 to 6 gigahertz spectrum, different spectral bands are also being researched. So, and these spectral bands are typically about 24 gigahertz frequency, and the band which is particularly of interest is 28 gigs, around 28 gigahertz. So I think, if I'm not mistaken, there are some deployments already happened in this band in countries like Korea. So yes, so 5G uses a broader spectrum, 5G broader bandwidth and a higher spectrum. And of course, this gives a boost in the throughput, right? But the point to remember here is different spectrum has different propagation characteristics. For example, the lower band of the spectrum, lower spectrum, they work well if you want to provide network to a wide area, because they are not, they don't get attenuated as easily as a higher frequency spectrum. But a higher frequency spectrum gives you uh, very high throughput, and also you can have in a small cell you can have a dense deployment. Um, Typically very suitable if you're having like thousands of sensors connected in a network, and all these sensors are in a manufacturing plant, for example. So for that, higher frequency bands are extremely suitable. So 5G supports both, and 5G uh, takes advantages of both the bands and the propagation characteristics. And of course, because 5G works on this wider band, it has a very high throughput, right? So that's it. 5G is fast because it uses wide band in a high frequency spectrum. So it has a high, bigger bandwidth, and its throughput is very high. So that's fast, right? So that basically answers the question why 5G is fast. Nope, not so fast. There are a few other things. So let's ask the question. So if you use 5G technologies in a 4G band with the same bandwidth, whether still you will get a better throughput, right? So the answer is yes, we do. So, so what makes 5G special, right? So one of the key technologies in 5G which helps in increasing the throughput is carrier aggregation. So I will not go very deep into carrier aggregation details, but you can imagine a carrier is something, an RF resource using which data is transmitted. So you can think of as an RF channel in a particular frequency spectrum or frequency band in which the data is transmitted. So there, in a cell site, you will have multiple carriers, and each carrier is basically tuned to a particular receiver. So your mobile is tuned to a carrier, and you basically receive data over that carrier. Now, carrier aggregation is a technology which basically combines. So if you're in a cell site and if you're using your mobile, and if there are some free carriers, so these free carriers can be combined to give you increased channel bandwidth and increased throughput. So this technology was already exists in 4G as well, but 5G kind of took this technology into a different level. So what 5G did is the technologies or the innovation in 5G is basically the receivers and transmitters can do a carrier aggregation of different carriers with different characteristics, which means so if there is a carrier in a lower frequency band or in a higher frequency band, and a carrier in a higher frequency band, they can be aggregated, which was not possible in 4G. And also carrier from two adjacent cells can be aggregated, which is not possible in 4G. So if your receiver can receive, if there is overlapping signals from two adjacent cells, and a receiver can use carrier aggregation by combining carriers from adjacent cells. This is also called dual connectivity. So dual connectivity is one of the key things which enables 5G to work with the 4G RF as well. So you have a 5G enabled device, and you are moving through 4G and 5G coverage areas. This dual connectivity and carrier aggregation helps in increasing the throughput of the device by combining different carriers of different RF numerologies. So another key innovation which improves the throughput, is beam-centric design. The 5G RF, or which we call RAN, RAN, which stands for radio access network. So the 5G RAN is designed considering the multi-antenna structure, or we call beam-centric design. So every receiver and transmitter antenna in 5G, they are not a single antennas. They are it's an antenna array, and each element in the antenna array can be controlled, and can create the transmission beams or receive with different characteristics. And this is basically the key innovation, which enables 5G to support various different use cases and adapt to various different conditions. So, for example, at a high frequency, if 5G is working in a high frequency band, then these antennas, to minimize the attenuation loss, the beams of these antennas can be of smaller width, and the antenna can employ something called beam sweeping to kind of compensate for that, and the receivers can then navigate the entire spectrum to find out where those signals are coming from. And similarly, in a low frequency, we can use massive MIMO. MIMO stands for multiple input, multiple output technology, and this technology existed before 5G also. This is not something invented in 5G, but 5G uses this technology and has something called massive MIMO. So where each of which relates to the carrier aggregation we talked about earlier. So each of the receiver antennas can basically take the so each antenna here, a transmitting antenna, can basically focus on a single receiver antenna. So you get many devices in the particular cell can be serviced by each of these antennas. So it supports a dense deployment with massive MIMO functionality, and of course it can with carrier aggregation, it can give a very high throughput. So yes, so these two key technologies improves the 5G throughput, even in the same band as 4G. So of course, if you have a larger band, you have larger bandwidth, your throughput automatically increases. But along with these technologies, the 5G can give extremely high bandwidth and support the very high speeds data transfers. Now, there are some other things which enable 5G to provide very high throughput. So in 4G, you have a lot of always-on signals, because that's how the receiver, your mobile phone, or for example, can automatically connect to a 4G carrier and lock into a 4G signal. So there are a lot of always-on signals there, but every aspect of the protocol has been relooked in 5G, and the always-on signals are minimized to a large extent. So the band is generally free. So if there are no data transmitted, there are no demodulation reference signals sent. So this allows for increased spectral efficiency of the band. Another key is 5G supports dynamic time division, TDD. So what happens in 4G is, if there is an uplink and downlink happening, the RF resource allocation happens before, and you cannot change that. So if you're downloading something, or even if you're uploading something, the resource which you get, RF resource which you get for downloading, uploading, it's not dynamic. It will not change as per the need of the user. But 5G supports that if a user wants more upload bandwidth or more download bandwidth, that could be managed. And this again gives a better throughput experience. Okay, so we talked about throughput, and we at least got an overview of how 5G can improve the throughput. Now let's talk about latency. So this is a frame structure of one time domain signal. So typically you have a 10 millisecond frame, and the data is sent in 10 millisecond frames, and this is one subframe of 1 millisecond. So there is 10 subframes sent in 10 millisecond. I will not go very deep into it. I just want to explain one technology here, which kind of drastically reduces the latency, which is basically mini slots transmission. So if you see here, each subframe have slots. So the one slot is nothing but a modulation, OFDM modulation, which has 14 symbols. So one slot has certain bandwidth. So in every slot, the data is sent in slots. So in 4G, the slot spacing is fixed at 15 kilohertz, and the data transmission can only happen at the start of the slot. So if there is a sender who has data, the sender has to wait till the start of the next slot and then send the data. But in 5G, the data is organized in such a way that you can send the data in between the slots. You need not wait for slot boundaries to start sending data. So this is also called mini slots. So you can send in mini slots. So any low latency application, when you want to send data, it need not wait for a slot boundary. It can send as soon as the data is ready, and it drastically improves the latency. And also the structure of the data here, all the reference signals are packed in the start of the data, and so the receiver and the transmitter, the buffering of the data is reduced, means they can start demodulating the data as soon as they receive the data. They do not wait for the entire data to be received and then get the reference signals and then demodulate. So some of these protocol improvements makes 5G enables 5G to support ultra low latencies. Okay, and as I said before, in 5G, we have every aspect of the protocol, every aspect of the transmission is been relooked and redesigned for ultra low latency as well as high throughput. So instead of during the retransmissions as well, instead of transmitting the entire transport block, 5G in 5G there is something called code block groups. So these are the packets of data which are of finer granularity than the entire transport block. So only that part of the data is retransmitted, so not the entire block. So this again improves the latency. Also, in the throughput section, I mentioned that it supports dynamic TDD, where you can dynamically change the RF resource allocation based on the need. But also, it can support a fixed or a RF resource allocation. Because in certain low latency applications, what the device needs is just to be told, okay, use this RF resource and do the transmission. You don't have to figure out dynamically what RF resource you got. So you save some time in transmission. So you can have this configured as fixed RF. You can configure a particular device to use a fixed RF resource. Okay. So in summary, Wi-Fi is fast. So yes, of course, you have a wider bandwidth and higher spectrum, and you get a higher throughput. But also, every aspect of the 5G stack is kind of relooked and redesigned, and with stuff like carrier aggregation, massive MIMO, beam-centric radio, 5G provides extremely high throughput. And also, the protocol itself, every layer in the protocol has been kind of relooked and redesigned for providing a much higher spectrum efficiency and very low latency. Examples like mini slot transmissions enable 5G to ultra low latency. Okay, so we are at the end of part 1. So if there are any questions, maybe I can take some now. Do we have any questions?
Yes, we do.
Sure.
Sparsh Jain asks, what is the current band in use for public use?
It depends country to country. I think very recently in India, there was a spectrum auction, which if I'm not mistaken, it was from 3900 megahertz to 4300. So it's now everything is between that 450 megahertz to 6 gigahertz range. And for 5G, it's closer to 6 gigahertz bands are being auctioned in different countries. I don't know the exact band which was recently auctioned, but it was something in that range. And different countries they use different bands, but in that spectrum.
Thank you. And do multiple carriers share the same band?
Yes. So there are two things there. So there could be carriers. So the band is allocated for the entire transmission. So and it's a very wide band. So the carriers are basically local transmission channels in a particular cell site. So they all fit into that frequency band. So yes, they share the same band. The thing is, you can combine. There are multiple carriers in a cell site, and you can combine them to kind of increase your channel bandwidth.
Okay, thank you. The last one right now is what is an example of critical data which causes async sending between slots, from Sid Raman Pant?
Oh, that's a interesting question. We will see one of the examples in this talk, but one example which kind of uses this very extensively is high frequency trading. So when you're doing buying shares or buying stocks, every milliseconds it matters. So high frequency trading is one of the applications, but we will see one more in this talk.
Cool.
Thank
and
you.
There's one more question as well,
Sure.
if you don't mind. Okay, if multiple carriers share the same band, why does Department of Telecom conduct auction for bands?
Okay, I think there is some misunderstanding here. So when you say carriers, so it's basically a OFDM modulated channel. So you can imagine as a basically RF resource which carries some data. Now the auction happens for the entire frequency bands in the spectrum. So there could be an auction happening for band between 3900 to 4400. megahertz. So that's an auction which government does, because this entire spectrum is owned by the governments. So they auction these bands to telecom companies, who can then lease out the band and use the band. So the carriers are something very different than the actual bands. So the carriers are basically an RF resource inside the bands. So I hope it clarifies.
Yes, to me. We'll see about the person who asked it. It's an anonymous question, but that's it for now.
Yes,
go ahead.
Let's move on. Let's see. I have quite a few things to cover. Let's try to speed up this a bit. Okay, so let's go to some interesting stuff now. 5G systems. So what you see on screen is the highly simplified version of 5G systems. So what we have in 5G is a 5G core and a RAN. RAN is radio access network. So your mobile devices or any 5G enabled devices connects to the RAN, and RAN basically connects back to a 5G core, which provide access to internet gateway. So and typically the RAN and 5G core are connected using high-speed fiber optical links. So now, but remember this is a highly simplified overview. I just want to give the context, right? We will be talking more about the RAN in this talk, and not the 5G core. Though I personally work more on 5G core, but as I said, this talk came out of my hobby, which I am working on RAN. So what is the basic what are the responsibilities of 5G core? So 5G core has lots and lot of services. So if you're interested, you can. I will have tons of material on internet. You will have different components in the 5G core. You can look into it. But basically what it does is it does mobility management, subscriber management, authentication. So basically your SIM card and everything, you are subscriber of some telecom service like Jio or Vodafone, whatever. So they have their 5G core or 4G cores. So your data is there, and whenever you are on the network, you are authenticated. So all these things and happens in 5G core. I mean, your subscriptions, all the management happens in 5G core. And also 5G core adds something like QoS and slicing to the existing 4G core. So QoS is something where quality of service, where in 5G core, you can define that for certain customers or certain cell sites, you need certain capabilities. So one thing you should remember from the part 1 of this talk is 5G is highly configurable, right? It can work in different bands. You can configure. You can have a fixed frequencies. You can have dynamic frequencies. You can configure it for ultra low latency. You can configure for bigger uplink or lower downlink, or the other way around. So different things 5G can be configured, and so 5G core kind of manages that what should be configured for what network, right? Now coming to RAN, RAN is basically the thing which implements those configurations. So all the policies set by 5G core. So RAN is something which basically connects to the physical layer, and basically ensures that all those policies are quality of services defined in the 5G core for different customers, different use cases are implemented correctly in the radio. So RAN also has different components, different services. We will see about that. So Uh, and also one more thing, so 5G core, there is a concept, it's logically divided into a user plane and, or in fact, the four or 5G systems, it's segregated into user plane and control plane. So this is a logical segregation. The idea is separation of concern. It's a good design philosophy. So control plane takes care of sending control signals to the RF nodes and the transmitter receiver, enabling the transmitters and receivers to kind of do the demodulation properly and error correction. So all those things, discovery, are managed through the signals sent in the control plane, and the user plane is where the data is handled. So there are services in the control plane, there are services in the user plane. The 3GPP community is very clear that these planes, the services and the devices in control plane and user plane are clearly defined so that they can evolve independent of each other. So I will be using these terms, and I hope I will be clearing them up once we see some examples. Okay, so let's see what is in RAN. So here is two different examples of RAN deployment. So don't worry too much about these abbreviations. I will try to clarify them. So 5G core, there are many more components than just these two. Here only these two are shown because these are the two components which interact with RAN. So RAN consists of something called GNB. So remember that GNB is a logical entity. There is no physical entity as GNB. It's a logical entity. What GNB does is GNB controls all the radio activity. All the services provided by RAN is controlled by GNB. So GNB can be like a standalone GNB here. So which has the antennas, which has the transmitters, which has all the software, all the services to talk back to the 5G core, and everything in one single physical node. So that is also one deployment of GNB. So when you see a 5G tower, maybe that's the GNB, and that's everything in there, right? So the more common way of deploying GNB is splitting the GNB into two, which is like a GNB control unit and GNB distributed unit. And typically GNB control unit is completely software, and this can be deployed in a cloud service, in a cloud somewhere. And DNB distributed units are the RF and the transmission part of this, which typically you see the 5G towers. So they are GNB DUs. So a single GNB CU can basically manage multiple DUs, and each DU basically consists of a cell site. So this is kind of a typical deployment. But we will see one more deployment in coming slides. Okay, and in the 5G core, the AMF is the access mobility function. So this basically takes care of so when a mobile phone connects through GNB to AMF, it basically authenticates, and when a user moves from one cell to other cell site, this AMF basically intimates the GNBs that the particular subscriber is moving, and all the needed authentication, everything this AMF takes care of. So this comes most under the control plane. So if you see the protocol with -C, that means it's basically a control plane signaling, and -U is basically user plane. So UPF is the user plane functionality service. Basically, this provides the connectivity, data connectivity to the devices over GNB. So we will not talk more about AMF and UPF in this talk, but yeah, so just for you to know that UPF kind of takes care of the data connectivity. So this just overview of this stack is we are just going to talk about the QoS here because we are going to refer to this. I have to put this in this talk because we are going to refer to this particular stack in the next slides, coming slides. So as I mentioned, there is something called QoS in 5G. So this particular stack is inside GNB. Okay, this is the RAM, and the QoS policy definitions are done in the core. So the core can say that, okay, for this particular, so it can define QoS like you can have a low latency QoS, you can have a very high throughput QoS, and it can have QoS for a very dense cell implementation where there are like thousands of sensors. So core can define different QoS, and those QoS data basically are read by this SDAP layer. So SDAP is Service Data Application Protocol layer. So what this does in the GNB is it has information of what are the RF channels, or it's called radio bearers. So there are so in a cell there are different radio bearers with different characteristics which can be configured. So as I said, if you want for something low latency, you have a prefixed channel assigned to it. So that radio bearer will do the low latency stuff. So there could be multiple radio bearers, and this SDAP kind of maps the QoS policy defined in the core to the correct radio bearer, right? I hope it makes sense. So this is this kind of so whatever in the core somebody configures, this SDAP basically makes it a reality by mapping it to actual physical radio bearer or radio resource. Rest of the stack is not very important now. So let's move forward. Now let me introduce the most interesting aspect of 5G, according to me, O-RAN alliance. I was not aware of this O-RAN alliance until a couple of years back. 3GPP, I think, is more common. Everybody knows. But O-RAN alliance is something which kind of complements 3GPP. So what O-RAN alliance does? So it's a community which is created by leading mobile operators and vendors and academics to basically provide an architecture, provide a RAN architecture for 5G, which can enhance and also fulfill all the 5G promises. So as I mentioned, as you've seen so far, 5G is highly configurable, right? 3GPP defines all the technologies, what can be done, how it can be done. Now, then there are user use cases, like a normal user, like you are doing some gaming, or you are doing some high frequency trading, you're purchasing some stocks or placing some bets, or you are doing a multiplayer gaming, or you're controlling a drone. So there are different use cases. So O-RAN kind of provides architecture or a framework which kind of enables these different use cases to be applied and to be implemented on a 5G network. Right. So O-RAN it's kind of complements 5G, 3GPP specifications. And the focus of ORAN is the complete implementation is implementation, and as well as the all the specification. It's free and it's open source, and the focus is everything is implemented in software. And also the focus is to provide a reference implementation of the ORAN architecture stack and components so that anyone can use it. There are several use cases defined, and I will be talking one of the use cases. So this gives, the idea is to give a very low entry barrier for anybody to entering into 5G. So hypothetically, any one of us, any one of software engineers can just read the ORAN specification, take the reference software, and create an ORAN app. We will come to that. What are those? And basically add more value to any 5G network, and you can actually monetize that. So it's fun and it's profit. So and it's, I have been trying this, playing around with this for a year, and it's amazing. And there are lots of startups who are taking this ORAN, because one of the goals is to have 5G or entering into 5G space should not be only for big companies. Everybody should be able to contribute as well as benefit from this. So let's enough of the pitch talk. Let's start looking towards ORAN. So this is the ORAN architecture. Don't get overwhelmed by it. Let me break it down. So the heart of the ORAN is something called RIC, which is RAN Intelligent Controller, right? And there are two types of RICs. One is non-real-time RIC, and then the other one is near real-time RIC. Why there is non-real-time and real-time? So near real-time RIC makes the control loop here, right? The decisions made by this near real-time RIC. It's approximately 1 second or a little bit more. So all the machine learning, and so ORAN focuses heavily on machine learning and uses heavily on machine learning technologies. So all the machine learning algorithms which are running somewhere, so all the inference of those machine learning algorithms and models are done in non-real-time RIC. So based on those trained models, this does some inferences, and the results of inferences are pushed as policies to the near real-time RIC. So the near real-time RIC basically directly controls the GNBs, which is CU, the central unit control plane, and the central unit user planes. So any RF, and this ORAN, you can set a policy specific to a single user in that network. So because it gets all this information, it can get the information about different users who are connected in the network, and it can, based on its machine learning algorithms or some other algorithms, it can say that, okay, for this user, these are the policies needs to be set, and it can push to the near real-time RIC. So here the control loop is in the range of 10 milliseconds, and then it basically controls the EGNBs on what radio parameters has to be configured to achieve those QoS, or here in ORAN language, we call it QoE, quality of experience. It gives that experience, not just the quality of service. And ORAN is fully compatible with 3GPP technologies. So all the interfaces which here you see, they are all 3GPP interfaces. So it can talk to a 3GPP core, it can talk to a 3GPP GNB components, other GNB components. So this kind of adds on to the 3GPP technologies. So these two layers which you see in red are currently implemented in hardware. So this is a distributed unit. So this is typically the antennas and stuff. The radio unit. So the radio unit is the antennas and this stuff, and distributed units are basically the things which control the radio unit. But there are research and very aggressive research on moving this ODU also into software. Currently it is not, but in near future it will be. So the entire stack, everything will be software except for the radio unit, where you basically need the antennas to do the transmission. So, so this is the vision of ORAN. And there is a O-Cloud specifications of ORAN where all these components are running on this O-Cloud, and this can be deployed. This is agnostic of any kind of deployment. So this can be deployed in your cloud, data center, wherever you want. So unsurprisingly, the near real-time RAC is the place where there's a critical timing constraints and stuff. And here comes our CPP, C++. So, sorry. So the entire framework of ORAN on the cloud side and on the non-real-time side, it's mostly written in Go, unfortunately. But the near real-time components, the near real-time RAC, the framework, it's mostly written in C, and many components are written in C++ as well. And there are bindings for other languages also, like if you want to write it in Rust, Go, or Python, you can do it. There are bindings, but the core is written in many of the core components are written in C and many in C++. So if somebody tells you that C++ is not used in newer technologies or newer projects, basically this is one example where it is used in cutting edge, bleeding edge technology. So let's go quickly. So I'm not, I think I'm very close to the finish time, but what I'm going to do is I'm not going to explain the entire thing. So what you need to understand is in the non-real-time RAC, there are something called RAPs. So so this is the framework, the different components in the framework. The framework is provided by ORAN. The specification is provided by ORAN, and there is a sample implementation provided by ORAN. Anybody can take that and write RAPs. So RAPs could be implementing anything, like it can do. Some of the examples are it can see the historical data of that particular cell, and it can do a cell utilization predictor, which means it can say that, okay, during this time of the day, of the year, the number of users are more dense in this cell. So during this time, it can tell the RF GNBs that, change your policies dynamically during this time of the day, and in some other time of the day, you can do something else. So you can create an RAP to do that. So, and it can be deployed. So similarly, you can do a signal predictor. So if you know that if there is a car or something moving in that area, so it's a hilly region. So the predictor can detect that if that user device is moving in a certain direction, then it's going to fade. Then you do a handover to another cell immediately. So those are some of the interesting applications based on machine learning you can create, and you can write these RAPs and show. Similarly, for near real-time RAC, similar to RAPs, these are called XAPs, the same idea. But as I mentioned, the control loop is very fast here, less than 10 milliseconds. And here, basically, it controls the radio resource manager. So you can set the policies in the resource manager dynamically based on the requirements. So these are some of the references. So yes, its talk is not complete without a code. So XApp, a simple, this is a C++ XApp. So you basically, it's very simple to do. You register, you create an XApp, you register you create a callback. This is the callback signature. You register the callback and you run the app. So the callbacks will be called with messages from different RF components. So you then process the message and then you can write back. So this is all you do. You basically see the messages and see what's happening, and you can write back the policies and control the RF. So this is an XApp. So you can write your own XApp and deploy. So here is a RAN use case. We'll quickly go through. So here you have two UAVs, which has some cameras, which probably manning a boundary for security applications or defense applications. And they are sending the image and video data continuously to your, uploading it somewhere using the GNB, using the 5G network. And here you have an anti-weapon UAV and a mobile control station. So this station identifies if there's an illegal UAV flying around, and it sends control to this messages to this anti-UAV weapon, which basically destroys this. So in the same single cell, there are multiple use cases here, different service use cases. So for this UAVs, the use cases, it has to do a very high bandwidth upload because it's sending real-time data, real-time videos, streams. But for this UAV, anti-weapon UAV and mobile control center, it does not care about the data throughput because it's the data is control data is very less bandwidth, but it cares about the latency. So you need a very low latency here because it has to send signals immediately to destroy this UAV. So using normal 5G, you can do this by creating different quality of service, but it's very difficult to do it in a single cell where there are different quality of service requirements for different UEs. But with Open RAN coming in, you can have a non-real-time RT monitoring the different UEs and set policies and tell a real-time RAC that for particular UE, what policies has to be set, which basically is set here. There are two ways of doing it. One is where everything, even the core, everything is in a single location. The other way where the core is some other data center and only the ORAN components are in this location, basically a GND. All right. So sorry, I have to rush through them. So connecting the dots. So 3GPP and 5G and ORAN, they kind of complement each other. You can write your own RFs and XApps, and it's profit. And I would encourage people to go and look at it, go to the references, look at the code. You can, most of them C++ developers will all be at home because its framework is written in C and C++, so you can use it. I hope I will be doing another talk where I actually write an XApp and demonstrate. Okay, thank you. Thank you for being with me. If there is some time, I can take some questions.
Thank you very much, Selva. We have just one question. I guess we'll take it. So if 5G core acts on the internet, most of the world is moving to IPv6. What is the status?
Yeah, 5G core supports IPv6. So it's ground up built using IPv6. So that should be should not a problem. So
yeah. All right, that's it in the questions.